this video, we discuss other types of Sturm-Liouville problems. Specifically, in this video, we'll be discussing periodic Sturm-Liouville problems. I'm going to call this 3.2.1. We'll also discuss singular Sturm-Liouville problems, but not in this video. We'll do that next time. So the plan is this. First, we will define periodic Sturm-Liouville problems. We will note some differences and similarities. Between the regular Sturm-Liouville problems that we've been discussing and these periodic problems. And then finally, we will find the eigenvalues and eigenfunctions of a particular periodic Sturm-Liouville problem. And the example that we're looking at actually allows us to derive the formula for the full Fourier series of a piecewise smooth function. So this example is not only an example of how to solve one of these, it is a derivation. So it's a derivation of the full Fourier series expansion. Of a piecewise smooth function U, defined on an interval from negative L to L. Okay, that's the plan. Now let's start with the definition. One thing I want you to notice right away is that the differential equation hasn't changed. P is continuously differentiable and given to us, excuse me. Q is also given, sigma is given. If we can write the differential equation in this form and we have that differential equation for x values in some finite interval starting at x equals a and ending at x equals b, and we have these two boundary conditions, then what we have is a periodic Sturm-Liouville problem. Now I want you to notice the difference between these boundary conditions and the boundary conditions for the regular Sturm-Liouville problem. So the boundary conditions for the regular problem look like this. Remember that we require kappa 1 and kappa 2 to not be both equal to 0. Struggling a little with my grammar there, you know what I mean? They can't be 0 at the same time. And then kappa 3 and kappa 4 can't be 0 at the same time. Notice that the first condition talks about the function that we're looking for, the solution to the boundary value problem, at its left endpoint, on the left endpoint of the interval. So this is telling us how the function value and its derivative are related to each other at x equals a. And this condition tells you how the function value and the derivative are related to each other at x equals b. This is a little different. This is relating the function value at the left endpoint to the function value at the right endpoint. And this is saying whatever function value we start with, that's the function value we end up with once we get to x equals b. And then this is saying that the slope at the left endpoint is equal to the slope at the right endpoint. So that's why we're saying it's periodic. The function is actually repeating itself. Whereas over here, there's no requirement that that function repeat itself. This is just telling us how f and its derivative are related to each other at one side. And this is telling us how f and its derivative must be related to each other at the other side of the interval. But this is different. So that's what makes this periodic. Now, a couple of other notes. When we look at the differential operator L, defined by L applied to f equals p times f prime, and then you take that product and take its derivative, and then add q times f. So that this piece right here is our linear differential operator applied to our function f. That linear differential operator is symmetric on a space of functions chi. And remember, we really want that to be true. When chi is the space of functions, and let's say they're the space of twice continuously differentiable functions, or let's just say twice differentiable. I don't think it said continuously differentiable in the text, but it's a space of twice differentiable functions that satisfy the new boundary conditions. So f of a is equal to f of b. So we start and stop at the same function value. And the slope at a is equal to the slope at b. And remember what that means. If that operator is symmetric on the space of functions x that we're interested in when we're solving that problem, that means that we get all of the results of theorem 3.8. Those results related to the eigenvalues and eigenfunctions of the particular problem that we're interested in. So that means theorem 3.8 holds. Now remember what theorem 3.8 said. Theorem 3.8 said the following: we're going to have this increasing sequence of eigenvalues, infinitely many of them. It also said that the limit as n goes to infinity of the nth eigenvalue is infinite. So lambda sub n goes to infinity as n goes to infinity. And finally, the eigenfunctions are, let's just say, mutually orthogonal with weight sigma. Again, sigma is that function that is multiplying f and the lambda in the differential equation when it's written in this form. Now, one thing that you should notice, or one thing that you should note that's a little different when we're talking about the periodic problem versus the regular Sturm-Liouville problem, is that this time when we're studying the periodic problem, the eigenfunctions, or we don't get exactly one eigenfunction for each eigenvalue. In this case, it's possible to get two linearly independent eigenfunctions for a single eigenvalue. Remember, there was a different theorem, it wasn't theorem 3.8, in which we said that every eigenvalue corresponds to exactly one eigenfunction. It's not the case when the problem is periodic. So let's write that down. So I'm saying that when we're dealing with a periodic Sturm-Liouville problem, Sturm-Liouville problem, a single eigenvalue may correspond to two linearly independent eigenfunctions. Instead of calling those f sub n, we'll call them f sub 1 of n and f sub 2 of n, corresponding to that eigenvalue lambda sub n. Okay, but still, we will always be able to choose a pair of eigenfunctions that are orthogonal with weight sigma on the interval from A to B. So given that choice, we're still going to be able to construct eigenfunction expansions or a generalized Fourier series for a particular piecewise smooth function U using our orthogonal functions. It's just because we've got two eigenfunctions here, or possibly two eigenfunctions here for a single eigenvalue, we can't just say that this set of eigenfunctions is orthogonal, because we actually have two sets of eigenfunctions. So it gets a little tricky, but we'll always be able to choose a pair of orthogonal eigenfunctions with the appropriate weight so that we can construct an eigenfunction expansion of a function U. So that's a lot of, I did a lot of talking without a lot of writing. So let's write that down. We can always choose eigenfunctions f sub n and f sub m such that the integral over the interval of interest is equal to 0 on that interval I. Once we've made those choices so that we've chosen eigenfunctions that are orthogonal to each other. Let's say after making those choices, we can still construct an eigenfunction expansion, otherwise known as a generalized Fourier series expansion. Oops, there we go. Of a piecewise smooth function U. Okay, so those are our notes. That was a lot. I do want to briefly recap before we work our first example. So I want you to notice that the boundary conditions for the periodic problem are different from the boundary conditions for the regular problem. The boundary conditions for the regular problem specify relationships between a function and its derivative at one endpoint and the function and its derivative, the solutions that we're looking for in their derivatives at the other endpoint, but it treats the endpoints like separately. It deals with the function value and its derivative on the left, and it deals with its function value and its derivative on the right. But with a periodic problem, we're talking about how the function value on the left and the function value on the right are related to each other. So here we're saying that they're the same, and here we're also saying that the derivatives are the same. So the function values in this are the same, and their slopes are the same. So that means this function is repeating itself, as I'm repeating myself right now. And so we've got a periodic Sturm-Liouville problem, and that means our eigenfunctions themselves would be periodic functions if we were to extend them to the entire real line, which we won't. We're actually just going to stick to the interval from A to B. Okay, so we know that that's true. Now, we also said that this operator L, the operator that gives us this, L applied to F equals this plus this little piece equals 0. That operator is symmetric on chi, where chi is a space of twice differentiable functions, just so that F double prime exists, that satisfy our boundary conditions. That means, since we are dealing with a symmetric operator, that theorem 3.8 holds. Now, theorem 3.8 says the following is true. We've got an increasing sequence of eigenvalues As n goes to infinity, the eigenvalues go to infinity, and the eigenfunctions are mutually orthogonal with weight sigma, but let's put a big asterisk there. It's like yes and no. Yes, we will always be able to find eigenfunctions that are mutually orthogonal with weight sigma, but when we're dealing with a periodic problem, a single eigenvalue may correspond to two linearly independent eigenfunctions. So things are a little different here, but even though that's true, we'll still be able to choose two eigenfunctions that are orthogonal with the appropriate weight. Given that choice, we can still construct our eigenfunction expansion of a function u. Remember, the eigenfunction expansion of u looks like this. But this may be a little different, maybe not, rather than starting with n equals 1, we might start with n equals 0. If we've got two sets of eigenfunctions, f sub 1 or f sub 1n and f sub 2n, rather than having just a c sub n here, we might have a c sub 1n and a c sub 2n. So we're going to be able to do something like this. It's just going to vary a little bit, but the idea is the same. Basically, we'll be able to take a weighted sum of the eigenfunctions here and the eigenfunctions here, add those together, and that will give us u whenever u is continuous, and it will give us the average of the limit from the left and the limit from the right at any jump discontinuity on the interval of interest. So this is what we did before when we looked at eigenfunction expansion. It's going to look a little different, but the idea of just taking the eigenfunctions and multiplying them by constants and adding them together and using that to get u, or something very closely related to u, that still holds when we're dealing with a periodic problem. Okay, so now let's actually solve this periodic problem. This is example 3.26 in the text. Now in the text, Dr. Constanda uses the Rayleigh quotient to rule out some values of the eigenvalue, eigenvalues lambda sub n. We won't be doing that. We're just going to start from first principles, look at all the possible values of that real parameter lambda, and then we'll see that for this particular periodic Sturm-Liouville problem, we end up deriving the full Fourier series expansion of a function u. So here's a problem statement. It says, find the eigenvalues and eigenfunctions of the periodic Sturm-Liouville problem. And this time our differential equation is f double prime plus lambda f equals 0. And we're interested in the interval from negative L to L. And we're told that at negative L and at L, the solutions that we're looking for have the same value. The y value on the left and the y value on the right are identical. We also want the slope to be the same when it starts and when it stops. Okay. All right, so we'll solve this problem in the same way that we solved the other problems, other regular Sturm-Liouville problems from first principles. We will start by solving the differential equation and then looking at the various cases for different values of lambda. Just like if we were to solve an initial value problem in an ODE class, we would start by solving the differential equation. We're doing the same thing here. So we've got this. We've done several examples like this already. Actually, I think we only did 2 examples where that was our differential equation. Notice that it is a constant coefficient differential equation. Lambda is just a real constant. Of course, the coefficient of f double prime is an implied 1. since it is a homogeneous, linear, ordinary differential equation with constant coefficients, we can start by letting f of x equal e to the mx and find the values of m that cause this function to satisfy that differential equation. In order to find those values, we'll compute the first and second derivative. The derivative of e to the mx is e to the mx times the derivative of the inside. That's a constant times x. The derivative of a constant times x is just our constant. Take the derivative again, bring your constant down, then multiply by the derivative of e to the mx again. Derivative of e to the mx is e to the mx times an extra m. Then we substitute that function and its derivatives into the differential equation. So we're going to have m squared times e to the mx plus lambda times f, which we assume to be e to the mx, and that's equal to 0. Factor out that e to the mx. And then we've got this. That's our characteristic equation. Now, if you want to, you can go straight from the differential equation to the characteristic equation. But again, I highly recommend that you write out all of these steps if you don't know where that characteristic equation comes from. I find that many differential equation students will get used to memorizing that we go from here to here, but they often cannot tell me where this comes from unless I have everybody show this work. So show the work if you need to, but if you know where it comes from, you can skip the steps. I'm just writing out my steps on the side. And now we want to solve the characteristic equation for m. So I've got m squared plus lambda equals 0. Let's subtract lambda from both sides. And I want to get m by itself, so I will take the square root of both sides. Don't forget the plus or minus on the right. And then we've got two roots, m1 and m2, which are given by plus and minus square root of negative lambda. Now, the nature of the solutions really depends on the nature of this expression, plus or minus the square root of negative lambda. And the nature of that expression depends on the values of lambda. So there are actually three cases. In the first case, this expression under the radical would be positive. So if negative lambda is positive, that of course implies that lambda itself is negative. If this is a positive number, then I can take its square root and I get a positive number, and I'll have m1 and m2 are equal to plus or minus the value of that positive constant. So we'll have distinct real roots in that case. This second possibility is that the expression under the radical could be 0. So lambda might be 0. In that case, m1 and m2 are both equal to plus or minus the square root of the opposite of 0, which is 0. So m1 and m2 are 0. So they're the same and they're both real. So we call that a repeated real root. And then the third case is this. It's also possible that negative lambda is negative, which would mean, of course, that lambda is positive. In that case, I'm taking the square root of a negative number, so I would end up with complex conjugate roots. Now from here, we're going to look at each case separately. We're going to find the general solution to the differential equation, and then think about which solutions satisfy the boundary conditions. First, we'll find the general solution to the differential equation in case 1, where negative lambda is positive, which implies that lambda is negative, which implies that lambda is equal to negative 1 times some positive value, which I'll call lambda sub star, where lambda sub star is positive. In that case, my characteristic equation, m squared plus lambda equals 0, can now be written this way. That's m squared minus lambda sub star equals 0. So m squared equals lambda sub star. So m1 and m2 are both equal to plus and minus the square root of this positive constant. Now you could write your solutions as e to the positive lambda sub star times x and e to the negative lambda sub star times x, because we've got two distinct real roots here. But anytime you've got plus or minus a constant, rather than taking e to the kx as solution, where k is the constant, and e to the negative kx as the second solution, I always recommend, or I often recommend in differential equations especially, that we write our answers in terms of hyperbolic sine and hyperbolic cosine. So we're going to choose to let our first linearly independent solution be hyperbolic sine of the square root of lambda sub star times x, and our second linearly independent solution be the hyperbolic cosine of the square root of lambda sub star times x. If you're saying to yourself, how is that related to that e to the mx that we started with? Remember, hyperbolic sine is 1/2. Hyperbolic sine of an angle is 1/2 of the quantity e raised to that power. Actually, it's not an angle. The hyperbolic sine of a number is 1/2 times the quantity e raised to that number minus e raised to the opposite of that number. In our case, the number would be lambda sub star, or square root of lambda sub star times x. So this is a linear combination of the two solutions that we would typically associate with these two distinct real roots. Here's our first solution, and there's our second solution. And this is saying that if I take the first solution multiplied by 1/2, I take the second solution multiplied by -1/2, and I add them together, that's just going to give me the hyperbolic sine function. Because this is a solution and this is a solution, a linear combination of those solutions is also a solution. So I can use this as one of my linearly independent solutions rather than using this as one of them and this as one of them. And the hyperbolic cosine function, similarly, is this linear combination of those two functions. Okay, so we're going to use those as our linearly independent solutions. Therefore, our solution to the differential equation is C1F1 plus C2F2, which is C1 times the hyperbolic sine of that number, plus C2 times the hyperbolic cosine of that number. So we just find M1 and M2. Find two linearly independent solutions, F1 and F2. You can use the exponentials if you want to. I recommend using the hyperbolic functions. And then you're going to state the general solution in the case where lambda is negative. And it's just a constant times the first solution plus a constant times that second linearly independent solution. Now from here, we're going to use our boundary conditions to solve for C1 and C2 to find members of this family of solutions that solve the boundary value problem. Okay. Now our boundary conditions for this example involve the function at the left endpoint and the right endpoint, and its derivative at the left endpoint and the right endpoint. So we're going to use the derivative anyway. It's helpful or convenient at this point to compute that derivative. So I'll compute it. Bring your constant down. The derivative of hyperbolic sine of a function is the hyperbolic cosine of that function. And I've got a constant times x inside. The derivative, or the derivative of hyperbolic sine of a constant times x is hyperbolic cosine of that constant times x times the derivative of the inside by the chain rule. Then we add, bring that C2 down, and we multiply by the derivative of the hyperbolic cosine. of that expression there. The derivative of hyperbolic cosine is hyperbolic sine of the inside function times the derivative of the inside. The derivative of a constant times x is just the constant. Okay, so we've got f of x and we've got f prime of x. And now we can use the boundary conditions to come up with a couple of equations. Our first boundary condition tells us that f of L and f of negative L have to be equal to each other. So the first thing that I will do is I'll find f of L. I'm just substituting in x equals L here. And then I'll also substitute in x equals negative L. Oops, I forgot my H. It's hyperbolic sine, not sine. And then eventually we will set those equal to each other and try to simplify the equation. But one thing I'd like you to notice is that you've got the hyperbolic sign of an expression and hyperbolic sign of the negative of the same expression. And the same thing is happening here because I've replaced x with L and I've replaced x with negative L. So I see something that looks very similar, but it may not be clear on the surface how we can simplify that. It's actually really easy to simplify. Once we remember some properties, or if we don't remember these properties, once we derive the properties of hyperbolic sine and hyperbolic cosine. So let's remember this. We know that the hyperbolic sine of x is 1/2 of e to the x plus, or excuse me, minus e to the negative x. Now, if I replace x with negative x, I'd have 1/2 of e to the negative x minus e to the opposite of negative x. Negative x is just positive x. So that's going to be 1/2 times e to the negative x minus e to the x. Notice that this is almost identical to this. They're just reversed. They're flipped. So if I wanted to, I could factor out a -1 and then write these in the reverse order. So this would be -1/2 times e to the x minus e to the negative x. So I've got -1 times the original hyperbolic sine function. And that is the definition of an odd function. You go x units to the left from 0, you go x units to the right from 0, you look at the y values are the same, but with opposite signs, SIGN signs. And actually, I think if we look at a hyperbolic sine graph, which looks roughly like this, that makes intuitive sense. So this is saying, go x units over here, find the y value. Go x units over here, find the y value. Those y values are going to have the same magnitude, but with opposite signs. If this was y equals 10, that's going to be y equals -10. This is at x equals -x, and this is at just an x value. That is not a negative. That's just a little, one of those little dashes that I'm using for that curve of -1/2 e to the negative x. Okay, so sine is an odd function. So if I see hyperbolic sine of a negative value, it's not factoring, but you can kind of think of it like factoring. You can bring that negative outside because the hyperbolic sine function is an odd function. The hyperbolic sine of negative x is -1 times hyperbolic sine of x. So this right here can be rewritten this way. I can bring that negative outside. So this will be -1 times hyperbolic sine of the square root of lambda sub star times L. Okay. Now, similarly, hyperbolic cosine turns out to be an even function. This is 1/2 of e to the x plus e to the negative x. I think it's almost obvious that if I replace x with -x, I get 1/2 e to the negative x plus e to the opposite of -x. Negative x is just positive x. That is exactly like that, just in the opposite order. Addition is commutative. So that's hyperbolic sine of, or hyperbolic cosine of x. So hyperbolic cosine of negative x and hyperbolic cosine of x are the same. So hyperbolic cosine is an even function. And I think if we look at the graph of that, again, it's sort of intuitively obvious. We look at what's happening geometrically. Hyperbolic cosine looks like this. Go x units to the right and x units to the left. Look at the y values. Since this is equal to this, the y values are going to be exactly the same. So if you go over here and y equals 10, you go over here, you're going to get y equals 10 as well. So that means that if hyperbolic cosine of negative x is the same as hyperbolic cosine of positive x, I can ignore this sign. This is the same as the hyperbolic cosine of a positive square root of lambda star times L. Okay, so that is our second boundary condition, simplified using the fact that hyperbolic sine of x is odd and hyperbolic cosine of x is even. Now, the boundary condition actually says that f of L and f of negative L are equal to each other. So let's set those equal to each other and solve. So we're going to have C1 hyperbolic sine of the square root of lambda star times L plus C2 hyperbolic cosine of the square root of lambda sub star times L equals -1 times C1 times the hyperbolic sine of the square root of lambda sub star times L plus C2 hyperbolic cosine of the square root of lambda sub star times L. Now, this term and this term exist on both sides. So you can cancel them if you want, or if you prefer, and many students do prefer it, you can subtract that from both sides. And now from that subtraction, you can see that those functions are completely gone. That's gone and that's gone, so is that. And I've got two functions that are almost identical to each other, but one is positive and the other one is negative. So what I recommend is adding this to both sides. You're in a differential equations class, so of course you do not have to show this step. You're taking partial differential equations. You don't have to show this if you don't need to. But this gives us 2c1 times the hyperbolic sine of the square root of lambda sub star times L. And these guys reduce, so that's going to equal 0. All right, so here are your possibilities. I've got a product. This times this equals 0. So that means either 2c1 equals 0 or hyperbolic sine of the square root of lambda sub star times L equals 0. But remember where we started and what we're looking at here. We're on the interval from -L to L. Of course, L is not 0 because then our interval would consist of a single x value. This would just be telling me that f of 0 equals f of 0 and f prime of 0 equals f prime of 0. And the interval would be just 0, except it really wouldn't make sense for x to be in between 0 and 0 without a less than or equal to sign there. So L equals 0 is not possible. We're talking about an interval that has, has an actual length to it. Talking about this interval from here to here. Having said that, this is positive, and we are in the case number 1, where lambda is actually negative and lambda sub star is positive. So this is a positive number times a positive number, and we're taking a hyperbolic sine of that. Well, remember, hyperbolic sine looks like this. You can think of it again as a linear combination of these exponential functions. If the number that we substitute into this hyperbolic sine function is positive, we're going to get a positive number. We're not going to get 0. The only way that hyperbolic sine of 0 is 0, or the only way that hyperbolic sine of a number is 0 is when that number is 0. If x is 0, we get 0. Otherwise, we don't. So this never happens. So the equation has no solution. This particular equation has no solution. And that means our our little or statement here actually doesn't give us nearly as much freedom as we might initially think. It says this is true or this is true and this is never true. So basically it's saying this has to be true. So 2C1 must be 0, so C1 must be 0. Okay, we now know that C1 equals 0. Let's go to the second boundary condition. The second boundary condition tells us that f prime of L and f prime of negative L are the same. So let's compute f of L, or f prime of L. Here is f prime. So notice you get this square root of lambda sub star out front for both of these, and then you've got the hyperbolic sine and hyperbolic cosine functions. Oops, I'm replacing x with L. And then f prime of negative L is going to look the same, but rather than substituting x equals L, I'll substitute in x equals negative L. And then remember the even and odd properties of those hyperbolic functions. Hyperbolic cosine is an even function, so this is actually the same as the hyperbolic cosine of the positive square root of lambda sub star times L. And this is actually the same as -1 times the hyperbolic sine of the square root of lambda sub star times L. So this is equal to this. All right, now our boundary condition says that these two expressions have to be equal to each other. So this equals this. I notice that I have a lambda sub star from in everything, so I'll factor that out. This is f prime of L. And I'm setting that equal to f prime of negative L. Also factoring out that constant square root of lambda sub star. Of course, we can divide out that positive constant. And then I've got this term on that side and that term on the same term on the other side. If we subtract that term from both sides, those are gone. And I have terms that look almost identical. I will add that to both sides. And then we'll get 2c2 times the hyperbolic sine of this positive number is equal to 0. And it's just like this. The only way this product is 0 is if one of these is 0 and the hyperbolic sign of a positive number is always positive. So that means that C2 must be 0. So C1 is 0 and C2 is 0. So that means our f, our original function here, the solution to our differential equation, is 0 times this function plus 0 times that function. So f equals 0 is a solution of the boundary value problem. But it's not a solution, or it is not an eigenfunction because we are seeking non-zero solutions of the boundary value problem. I'm going to write that it is not an acceptable eigenfunction because it isn't. By definition of an eigenfunction, we're looking for positive, or not positive, non-zero solutions, not zero solutions. So that means, let's go back to our eigenvalues. That when we talked about case 1 where lambda is negative, there are no lambda that are negative. So we can say there are no negative eigenvalues. Okay. Alrighty, so that was case 1. Now let's look at case 2. Case 2 involved lambda being equal to 0. In that case, M1 and M2 are both are equal to plus and minus the square root of the opposite of 0, which is of course 0. So then our two linearly independent solutions are e to the m1x, which is e to the 0x or 1, and x times e to the m1x. So we just get an x. And that x comes from reduction of order, and that's how we handle it anytime we have a repeated real root like this. The first solution is e to the m1x, and all of the solutions after that come from just multiplying the previous solution by x. Since I've got two values of m that are both equal to 0, I get two linearly independent solutions. If this was m1, m2, and m3 all equal to 0, the first solution would be 1, the second solution would be x, and the next one would be x squared because we'd multiply by x again. Again, this is content from the ordinary differential equations class. If you want more background on that, check out those videos. We've got these two linearly independent solutions. So that means your general solution is c1 times 1 plus c2 times x. Okay, now we want to find the values of c1 and c2 that caused this function to satisfy the boundary conditions. So we'll look at the first boundary condition, which tells us that f of L and f of negative L have to be equal to each other. Well, f of L is this. It's just c1 plus c2 times x, where x equals L. So we just get c1 plus c2 times L. F of negative L is c1 plus c2 times negative L. Or of course, we could just call that c1 minus c2 times L. Now these two functions have to be equal to each other. So that's c1 plus c2 times L equals c1 minus c2 times L. We can subtract c1 from both sides. We can add c2 times L to both sides, and we get 2c2 times L equals 0. Okay, now L is positive for the reasons that we discussed before. We are looking at an actual interval of x values. We don't just want x equals 0, and it really wouldn't make sense because we don't even include 0. We don't include the end points of our interval here. So x is strictly, or L is strictly positive. So the only way that this is 0 is if c2 is equal to 0. Okay, so that means that f of x is now equal to just c1 plus 0 times x, or just c1. Now for the second boundary condition, we need to compute f prime. So I'll first compute f prime of x. The derivative of f of x is the derivative of a constant, which is 0, plus the derivative of this constant times x, which is just this constant. So f prime of x is just c2. And actually, we just found that c2 had to be 0. So I'll just write due to the first boundary condition, we see that f prime is equal to 0. So our second boundary condition says the following. F prime of L and f prime of negative L have to be equal to each other. Well, they're both equal to 0. Remember, if f prime of x equals 0, then it doesn't matter what we put in for x, we're going to get 0. So at x equals L, we get 0, and x equals negative L, we get 0. F prime of x equals 0 is a pretty boring function. It's just 0 all the time. So this just says that 0 equals 0, which is, of course, true, regardless of the values of our constants c1 and c2. So the second boundary condition doesn't actually tell us anything new. So that means that our solution is f of x equals c1 plus C2 times X and C2 was 0, so we just end up with C1. Now you can choose any value you want for C1. Because we are using this method to derive the full Fourier series expansion for U, we're going to choose C1 to equal 1/2. So that means our function is equal to 1/2 when our lambda value is equal to 0. Now we're going to end up with infinitely many lambda values. Instead of calling this lambda sub 1, because this is associated with lambda equals 0, we typically denote this lambda sub 0 or lambda naught. And then the function that goes with that, we indicate with a subscript of 0 or naught as well. So we've got this eigenfunction corresponding to this eigenvalue for this particular periodic Sturm-Liouville problem. Okay, now finally, we're at case 3. And in case 3, we have negative lambda is negative, which just means that lambda is positive. Whoops. And that means that M1, M2 equals plus or minus the square root of negative lambda is actually plus or minus the square root of lambda times I. So we've got complex conjugate roots here. Now you'll want to recall from your ODE class that if M1 and M2 are equal to alpha plus or minus beta I, where beta is non-zero, so we've got complex conjugate roots, then our two linearly independent solutions for a second order equation are e to the alpha x cosine of beta x and e to the alpha x sine of beta x. Those are two linearly independent solutions that correspond to those two complex conjugate roots, that complex conjugate pair. So in our case, that's exactly what we're dealing with. We don't have a real part, so it's implied that alpha is equal to 0. The imaginary part is just that positive number multiplying I, that's square root of lambda. So our two linearly independent solutions are e to the 0x times cosine of beta x. Beta is square root of lambda. That's just a 1, so this ends up being cosine of square root of lambda x. And our second linearly independent solution looks just like the first one, except instead of a cosine, you'll have a sine function. Now we can use those to construct the general solution to the differential equation. But remember, we're not looking for the general solution to the differential equation. We're looking for solutions to the boundary value problem. So we'll have C1 times cosine of square root of lambda times x plus C2 times sine of square root of lambda times x. We want to know what lambda would have to be and what C1 and C2 might have to be so that this function solves the boundary value problem. In order to figure that out, we're going to use our two boundary conditions. Now, our boundary conditions, our second boundary condition involved derivatives. I needed f prime of L and f prime of negative L to be equal to each other. So it's helpful to take the derivative before we even get started. So we'll compute f prime. Bring your C1 down. The derivative of cosine is negative sine of whatever's inside. The derivative of a constant times x is just that constant. Bring your C2 down. The derivative of sine of something is cosine of that something times the derivative of the inside by the chain rule. The derivative of a constant times x is that constant. So we've got our F and we've got our F prime. Okay, so now let's use the first boundary condition. First boundary condition says that F of L and F of negative L have to be equal to each other. Now this time, we're going to deal with a lot of the same things that we dealt with our hyperbolic sine functions. It was very helpful to note the fact that the hyperbolic sine function is an odd function, so that F of negative X and F of X don't have exactly the same Y values, but they have opposite Y values. It's odd. And it was helpful to see that the hyperbolic cosine function was an even function. So I just want to remind you of that again. Just not hyperbolic sine and hyperbolic cosine, but just sine and cosine. Sine is odd. That means sine of X and sine of negative X are related to each other. They don't have the same Y values, but the Y value on the left and the Y value on the right have opposite SIGN signs. And cosine is an even function. So if you take the cosine of X or the cosine of negative X, it doesn't matter. You go X units from the origin to, on the right and X units from the origin on the left, and then you look at the Y values. The Y values are going to be exactly the same. These are just even and odd properties of sine and cosine. Those will come in handy when we're simplifying these expressions, the expressions that we see in F of negative L. So let's write down our two expressions. F of L is this. We've got C1 cosine of square root of lambda times L plus C2 times sine times the square root of lambda times L. And F of negative L will look similar. But cosine is even, so cosine of -1 times something is the same as cosine of that same thing but positive. And sine is odd, so it's almost like we're factoring out a negative, but it's not factoring. It's just an odd property. And I don't mean that it's like unique or strange. I just mean, and I don't mean odd versus even. Well, actually, I do mean odd versus even, but not in the sense of numbers. You know what I mean in the sense. Sine is an odd function. Okay, so we've got F of L and F of negative L, and they have to be equal to each other. So I'll set this equal to this. Again, the algebra is so simple that you may do a lot of this in your head. And I highly recommend doing that. I show these steps for people that need them. And I know that not everybody needs them. Okay, so this term appears on both sides. If we subtract that from both sides, those are gone. If we add this term to both sides, if I add that over here, I'm going to have two of these. So we have 2c2 times sine of the square root of lambda times L equals 0. Now this is a product. I've got this times this equals 0. And that means either C2 equals 0 or sine of the square root of lambda L equals 0. Now the sine of square root of lambda L equals 0 whenever what's inside the sine function is a multiple of pi, because we remember that sine looks like this. At pi, we get 0. At 2 pi, we get 0. At 3 pi, we get 0. At 4 pi, we get 0. At all of the multiples of pi, we get 0. So sine of this equals 0 when this expression inside is a multiple of pi. Remember, lambda is positive and L is positive. So these are positive multiples of pi. So n is equal to 1, 2, and so on. Solving for lambda, we've got a square root of lambda is n pi over L. So lambda is equal to n squared pi squared over L squared. So either C2 equals 0 or lambda sub n equals this. Okay, so that's what that first boundary condition tells us. Now, I want you to notice that we're not forced to say that C2 equals 0 or that lambda sub n equals this at this point. If one of these is true, then this function will satisfy the boundary value problem. Only one of these would have to be true. So if this is true, if C2 is 0, our function satisfies, well, the first boundary condition in the differential equation. If sine of square root of lambda L equals 0, or in other words, lambda equals n squared pi squared over L squared, if that's true, then this function over here will satisfy the differential equation in the first boundary condition. But either one of these could be true. We're going to come back to that. That's where our two linearly independent eigenfunctions for a particular eigenvalue will eventually come from. So we'll hang on to that thought. We'll come back to it very shortly. Now let's look at the second boundary condition. Now the second boundary condition tells us that the derivative at the left endpoint and the derivative at the right endpoint have to be the same. Let's look at f prime of L first. Now f prime is right here. I'm just substituting in x equals L. And f prime at negative L is going to look almost identical. But instead of sine of this, I'm going to have sine of the same expression, but with an opposite SIGN sign. Same is true here. Replacing x with negative L instead of L gives us that. But sine is an odd function. Since sine is an odd function, it's almost like I can take that negative out. I'm thinking like, I'm almost thinking about it as factoring, but it's not really factoring. It's just the odd property of the sine function. That negative can come outside. We'll have this. Because sine is an odd function, that negative, or the negative from there that we can bring outside because sine is an odd function, the negative times the negative will give us a positive coefficient here. And cosine is an even function. So if I take the cosine of negative x or the cosine of positive x, either way, I'm going to get the same thing. So I can just ignore that negative. All right, now these two expressions have to be equal to each other. Okay, now this expression exists on both sides, so you can subtract it from both sides and it'll be gone. We can add this to both sides, so we'll have 0 equals 2 of these. And the only way that product equals 0 is if one of the factors equals 0 and lambda is strictly positive. So the 2 is positive, the square root of lambda is positive. The only way this is 0 is if C1 equals 0 or sine of square root of lambda L equals 0. And we know that that means that square root of lambda L has to equal n pi. Since square root of lambda is positive and L is positive, this is a positive number, so n pi has to be positive. So let's restrict ourselves to values of n that cause that multiple of pi to be a positive multiple of pi. And we know that if we solve for lambda, we're going to get n squared pi squared over L squared. Divide both sides by L and square both sides. Okay, now here is where you want to be careful. We had an or statement for both boundary conditions. This says C2 equals 0 or this is 0. This says C1 equals 0 or this is 0. So there are actually there are a few cases within case 3. So let's go through case number 3, which is what we're in, where lambda is positive. And then we're going to look at case number 3, part 1. You've got options. In order for this first boundary condition to be satisfied, this is 0 or this is 0. So let's say that C2 is 0. Now, if C2 is 0, then I go to the second boundary condition. I could have C2 equals 0 and C1 equals 0. In that case, the solution to the boundary value problem would be F equals 0. But F equals 0 is not a solution that we're looking for. We're looking for eigenfunctions. So that possibility is out. Now, the next possibility is that we might have C2 equals 0 from here. And then rather than C1 equaling 0, we would have this equals 0. And we know that this equals 0 and all of the other conditions that we've already stated about lambda and L and so on. That is equivalent to saying that lambda sub n is n squared pi squared over L squared. So in case number 2 or number 3, part 2 here, our solutions actually look like this. F of x equals C1 times cosine of the square root of lambda times x and lambda is n squared pi squared over L squared. We get C1 times cosine of n pi x over L in that case. Okay, so we get eigenfunctions from this. When lambda sub n equals n squared pi squared over L, f of x would equal any constant times cosine of n pi x over L. Now we'll choose for that constant to be equal to 1. And then we have this, f sub n of x is equal to cosine of n pi x over L for n equals 1, 2, 3, and so on. So these are eigenfunctions for our periodic Sturm-Liouville problem. Now the third possibility is this. We might have C2, rather than having C2 equals 0 here, we could have sine of square root of lambda L equals 0 from the first boundary condition. And from the second boundary condition, we might have that C1 is equal to 0. And this first condition and everything else we know about lambda and L and all that implies that lambda sub n is n squared pi squared over L squared. So we see that same list of eigenvalues that we had in this case over here. But this time C1 is equal to 0 rather than C2 being equal to 0 like we had over here. So in that case, f of x is equal to this. If C1 is equal to 0, we have 0 times this plus C2 times that. And we're replacing lambda with n squared pi squared over L squared. So we get C2 times sine of n pi x over L. So for this value of lambda, lambda sub n, I not only get this set of eigenfunctions or this eigenfunction, f sub n, I also get this eigenfunction. I get the cosine functions, and I also get sine functions for every value of n. We don't want this constant there. We're going to take these functions and multiply them by constants anyway whenever we do our eigenfunction expansion. So we like our eigenfunctions themselves to be as simple as possible. So we'll choose that constant to be 1. And then our eigenfunctions might look like this. Sine of n pi x over L for n equals 1, 2, 3, and so on. This is what I was telling you about before. We don't just get one set of eigenfunctions for every eigenvalue. Now we have two sets of eigenfunctions for our eigenvalues. So we might write f sub 1n for this first list of eigenfunctions, and we might write f sub 2n for the second list of eigenfunctions that go with these eigenvalues. Lambda sub n equals n squared pi squared over L squared, where n is equal to 1, 2, 3, and so on. Okay, so you might say, all right, what does that mean for eigenfunction expansion? The principle is the same. The notation looks a little different, but the principle is the same. If u is a piecewise smooth function, on the interval from a to b, then we can write u this way. It can be associated with this. The sum as n goes from 1 to infinity. Let's say of a sub n times f sub 1 n of x plus the sum as n goes from 1 to infinity of b sub n times f sub 2 n of x. And then we also had that extra term, remember, when in the case when lambda was equal to 0. So we should also have a constant times this function. Okay, now this looks a little odd, but it's not that odd. It's really very similar to what we talked about before with eigenfunction expansion. Here we're just saying, take all your eigenfunctions, multiply them by constants. For the right values of the constants, we can add them together. We get something that's very closely related to this function u of x on the interval from a to b. If u is continuous, we get u back, at least point-wise. This converges to u of x at that particular x value. If u has a jump discontinuity at a particular x value, we get the average of the limit from the left and the limit from the right at that jump discontinuity. This is the same thing. We just have two sets of eigenfunctions. So you've got constants times the first set of eigenfunctions plus constants times the second set of eigenfunctions plus this constant times the 0th eigenfunction that was associated with lambda equals 0. Now, if you want to, rather than using these labels a sub n and b sub n and c sub 0, sometimes people will write it like this. I think this is how it's written in the Constanta textbook. We'll have c sub 0 times f sub 0 plus the sum, then goes from 1 to infinity, of c sub 1n times f sub 1n of x plus c sub 2n times f sub 2n of x. I actually prefer this notation because it reminds me of the notation that we use every time we come up with that function f. We say it's a linear combination of f1 and f2. So it's just c1 f1 plus c2 f2. Same thing over here, c1 f1 plus c2 f2, but c1s are functions of n. The f sub 1s are functions of n. So we're adding this extra subscript n to say that those vary with n. Now, for our eigenfunctions and eigenvalues from that derivation that we just did, we did a lot of work, so let's find it. Page 2, what's that, page 5, here's page 3. First, we saw that there were no negative eigenvalues. In case 2, we found that we had one eigenvalue, lambda sub 0 equals 0, that corresponded to the eigenfunction f equals a constant. And we chose for that constant to be 1/2. So we're going to have 1/2 times c sub 0 here, plus the sum as n goes from 1 to infinity of c sub 1n times f sub 1n. If you're saying, what are the f sub 1n's? Well, where did that page go? Here they are. There are cosines of n pi x over L. And we've got c sub 2n, different constants, times the sines of n pi x over L. And that is the full Fourier series expansion of u of x. Okay. So now we have done that derivation, but okay, let's go back to the original eigenvalue problem and make sure we answered the question. We were asked to find the eigenvalues and eigenfunctions for the periodic Sturm-Liouville problem, and these were the eigenfunctions and eigenvalues, corresponding eigenvalues that we found. Of course, this is not the solution. The solution is in all of these pages, but the answer to problem, or this example problem, 3.26 in the text. Of course, in the text, it's not all worked out like this. Is we've got this eigenvalue when lambda sub 0 equals 0. We have the corresponding eigenfunction f sub 0 of x equals 1/2. And then when lambda sub n is equal to n squared pi squared over L squared, we have a pair of eigenfunctions. F sub 1n of x equals cosine of n pi x over L. And f sub 2n of x equals sine of n pi x over L. Now, we did not discuss orthogonality, but it turns out that this forms an orthogonal set and this forms an orthogonal set. And if we multiply any two of these together, where the number n multiplying this pi x over L inside is not the same, if we have sine and cosine functions, we also get 0. So we have the orthogonality for any two distinct cosine functions, any two distinct sine functions, and any sine cosine pair where the expression inside does not have exactly the same angle. So if this is m and n are not equal to each other. It actually turns out that over the interval from negative L to L, we actually get 0 even when n and m are equal to each other when we have the cosine and sine functions multiplying each other. I wasn't sure off the top of my head whether or not that was true, so I wanted to look it up. Often, if you're taking a partial differential equations class, these formulas will be given to you, but the reason why they're true, as far as why they're true geometrically, that's all shown in the earlier videos that I made about Fourier series. If you're curious about the algebra, you end up using the product to sum formulas from calculus 2 in order to do the computation necessary to get these results. The computation is relatively straightforward, but I think it's helpful to remember what these integrals mean geometrically and to derive these formulas or results by looking at graphs and thinking about areas and all of that jazz. So, okay. That's it for our discussion of periodic Sturm-Liouville problems. We are done discussing that right now. Next time we will talk about singular Sturm-Liouville problems. They're really interesting. I don't know if we're going to do a bunch of solutions to various cases for singular problems, but we'll at least explore what they are in the next video. Thanks for watching.